Hello guys, we will prove that no group is a union of two proper subgroups. Okay, so what is the statement saying? It is saying that give me any group G, it will not be a union of two proper subgroups of G. Okay, so I will prove it by contradiction. Okay, so we will assume the opposite. We will assume the contrary. So assume that there exists a group G such that G is equal to H union K, where H and K are proper subgroups of G. Okay. Now, first thing what we will note that K cannot be contained wholly inside H. Okay. K cannot be a subset of H. Okay. Why? Suppose K is a suppose K is contained inside H. Suppose K is a subset of H. Okay. Then H union K, it will be H, right? And this will be a proper subgroup of G. It cannot be equal to G, right? So that will be a contradiction. Okay, so K cannot be a proper subgroup of H, or it cannot be a proper subset of H. So what does that mean? So that means that there exists some K in capital K such that K is not in H. That's the definition, right? If K is a subset of H, then given any small k in capital K, this small k will be an element in capital H. Now, here we are saying that K is not a subset of H. So that means that there exists an element small k in capital K such that this small k is not contained inside capital H. Okay. Similarly, by same arguments, uh, H is not contained inside K. H is not a subset of K. Okay, what does that mean? That means that there exists small h in capital H such that H is not contained inside, or H is not an element in K. This much we are just observing this. Okay, now what happens to this HK? Okay, HK will definitely be there in the group G. That we know because H and K, small h and small k, ultimately they are elements in G. Okay, and how is the diagram? So it's a suppose that we are having a group G. Okay, and then what we are saying is we have subsets like this. Okay, H, this is H, and then we will also have K. Why is the intersection non-empty? Because both of them are subgroups. So at least the identity element will definitely be there, right? So the intersection is definitely non-empty. And we also proved that it cannot be, properly contained in, one cannot be properly contained in the other. So here we will have some small h and here we will have some k, just like this. But ultimately h and k are elements in G. So hk will definitely be there in G. Okay. Now our question is, can HK be there in H? Okay. Now why are we bothered about this? We know that group G is written as H union K. So take any element here, take X in G, then X has to be in H union K. That means X has to be either in H or X has to be in K. Okay, it has to be in one of them, right? So if we prove that X is in H, then we are done. X will definitely be there in G. Or if we prove that X is in K, still we are done. Now suppose X is not in H and X is not in K, then X cannot be in G, right? So that's why we are bothered about HK, where this HK is, because HK is clearly there in G. Now it should be in one of them. It should be either in H or it should be in K. So that's why we are bothered about this. Now suppose that HK is in H. Okay, so how will an element in the H look like? Suppose, see, here we are saying that HK, this is an element in capital H. So let HK be is equal to some H1, where H1 is in H, right? Because HK is an element in capital H, call it as H1. Okay, now H inverse will exist. H inverse is an element in H. Why? Because small h is there in capital H. Okay, so let me write that step. So what do we have? We have that small h is in capital H. Now H is a subgroup. It's a subgroup. So H inverse will also be there in capital H, right? So we can operate on both sides by H inverse, and then what will we get? We will get that K is equal to H inverse into H1. Now H inverse is in H, also H1 is in H. H is a subgroup, right? H is a subgroup, and so what will we get? H inverse H1 must be there in H. Why? Because since H is a subgroup, it will have the closure property. If we are taking two elements in H and if we are operating them, it will definitely land in H, right? So this H inverse H1 must be in H. What does that mean? This implies that K has to be in H, right? But that's a contradiction, right? Because we started with K being not in H. This is a contradiction. It's a contradiction. So why did we get this contradiction? Because we assumed that HK is in H. So HK cannot be in H. Okay. Now similarly, suppose that HK is in K. Okay. Then we will have that HK is equal to some K1. Okay, where K1 is in K. Multiply by K inverse on both sides, then we will get that H is equal to K1 K inverse, and K inverse is in K and K1 is in K. Now K is a subgroup. Okay, so again it will have the closure property, so we will have that H is in K. Again this is a contradiction, right? Because we started with the element H such that H is not in K. So what happened? Here we have that HK is not in H and HK is not in K. Okay, so HK cannot be there in H union K. Okay, but what is H union K, which is equal to G? So what happened here? But we know that HK is in G, and we arrived that HK is not in G, right? So we are getting a contradiction. Okay, so let me just restate what we have done. So what we did is we started with an assumption that there exists a group G such that it can be written as a union of two of its proper subgroups. Okay, call it H and K. We are assuming that G is equal to H union K. Okay, then we showed that H cannot be fully contained inside K. K cannot be fully contained inside H. So we can find two elements H and K such that H is not in K and K is not there in H. Okay, now we are concerned about HK because HK definitely will be there in G. Now G is written as H union K, so this HK must be either in H or in K, right? But then we showed that HK is not in H and HK is not in K. So we are getting a contradiction. So why are we getting a contradiction? Because our initial assumption is wrong. Okay, so such a group G cannot exist. Okay, so that means that given any group G cannot be written as H union K, where H and K are proper subgroups. Okay, so that is the first thing. Now we also had one another question. Can this be true if instead of two subgroups, I am considering three subgroups? That is, can does there exist a group G such that G is equal to some H1 union H2 union H3? Okay, can we write like this? The answer is yes. Okay, we will give an example. Thus the to say that such a group exists, it is enough to give one example, right? So consider the Klein 4 group. Okay, so what is the Klein 4 group? The Klein 4 group is nothing but the identity element, then 0 1 1 0 1 1. Of course, Klein 4 group have different representations. This is one of the representations. Now consider H1 is equal to the identity element and 1 0. Okay, so is H1 a subgroup? We have identity element. If we are taking any two elements and if we are adding it, we will get uh, H1. We are getting element in H1 only, right? Because take identity plus identity, we are getting identity. Identity plus this one will get 1 0. Now 1 0 plus 1 0, we will get this as 0 0, which is again present. Okay, so it is closed. Now what is the inverse of 1 0? It is again 1 0. So every element have inverse. So H1 is definitely a subgroup. Similarly, H2, I will take it as 0 0 0 1. Again, by similar arguments, H2 is a subgroup, and H3, I will take it as 0 0 and 1 1. Again, H3 is also subgroup. Consider H1 Klein for group K4 is actually H1 union H2 union H3, right? So for three subgroups, answer is yes. For two subgroups, the answer is no. Okay.